continue talking about integrals. Today, before start calculating the arc length or length of an arc, we're going to talk about improper integrals. In next calculus class, you're dealing with series, and one of the tests of convergence of a series is using improper integrals. So what is an improper integral? Objective improper integral. Very well. Here's a question for you. Suppose I ask you to find the area below the function 1 over x squared on the right-hand side of x equals to 1. So the question is, find the area below function 1 over x squared on the right side of x equals to 1. Very well. When it comes to integrals, our very first step is to visualize what we are dealing with. So let us graph it first. This is our function, 1 over x squared, and we are just dealing with the right-hand side of the graph. So take a look at this. On the right-hand side, here you have your x-axis. Well, here you have your y-axis. And this is your graph here. And it says on the right-hand side of x equals to 1. So x equals to 1. And we want to know what is this area. What is this area? Well, okay. So as you can see, it doesn't stop on the right-hand side. It just continues. What is this area? Is this a number? Is this infinity? Since the graph continues, you might say, hey, the area is infinity, but is the area equals infinity? Because the graph continues. Remember that it just says on the right-hand side of x-axis. X equals to 1, and it continues on the right side. So how do we calculate this area? Do we say the area is infinity? Very well. So we are mathematicians. We learn about techniques of integration. Let us start calculating this integral. We're not just relying on visualization and say, hey, based on the visualization, based on the intuition, we can calculate the area and it is infinity or it's not infinity. Let us actually calculate this area. So we know that the area is equal to the integral. There is this function, 1 over x squared. We're going to write this guy down, 1 over x squared. And since we are taking the integral with respect to variable x, we use dx. On the left-hand side, we have 1. And on the right-hand side, we have infinity. Let's see. Infinity. I have Other colors, infinity. So these types of integrals are called improper integrals. One of the boundaries or both of them are infinity. So how do we write this guy down? We write it this way. We say, hey, this integral is equal to, since here you have infinity, your upper limit goes to infinity, approaches infinity. So recall, when it comes to approaching infinity, you're getting back to elementary calculus, the concept of limit. So we're going to write this as the limit. Okay, nice. Limit of the integral 1 to L, while L approaches infinity. So instead of having upper limit as infinity, we're going to write it as L approaches infinity. We calculate this integral, then we take the limit. Okay, here you have 1 over x squared dx, which is super easy for us to calculate this integral. Very well. This is 1 over x squared, x to -2, so you get -1 over x. This is the limit of L goes to infinity of -1 over x squared over x to the first. X starts from 1 and stops at L. So let us plug in L, let us plug in 1, and then take the limit. So here you have the limit of while L goes to infinity. So -1 over L minus -1 over 1. Well, negative and negative, it is positive 1 plus 1. So what is this limit as L goes to infinity? As L goes to infinity, -1 over infinity, this is just 0. So what is this limit? This limit is equal to 1. But what is this guy? This is the area. So the area is equal to 1. This area is equal to 1. Note that this little areas here, they're getting smaller and smaller. They're approaching to 0. So we expect this area to be a number, to be a nice number, which calculation shows that it is equal to 1. Well, what if I ask you to find the area below y equals to 1 over x on the right-hand side of x equals to 1? What if we change the function? 1 over x okay. So 1 over x, here we have our graph. Let's graph it. This is our x-axis. We're working on the right-hand side of x equals to 1. So we're going to ignore left-hand side of the graph. X-axis, and here you have your y-axis. This is your function, the graph of the function. It behaves like this. Okay. Continues. And we want to know what's the area on the right-hand side of x equals to 1. So this is 1. This is the area that we want to calculate. What is this area? Okay. So we are calculating the integral, improper integral, 1 to infinity of function 1 over x dx. Well, let's apply the methods that we learned. First of all, since one of these boundaries goes to infinity, we're going to use limit concept. So this is equal to the limit of the integral 1 to L as L or T. Sometimes you can just change these variables. This is just a variable. L goes to infinity, so it's not important to use one variable. L, T, different variables. 1 over x dx. We already know how to calculate this definite integral. Here you have your limit. Let us copy down the limit as L goes to infinity. This is the integral of ln. So we have ln of absolute value of x, and x ranges between 1 to L. There you go. Okay. So I have the limit of as L goes to infinity of ln of L minus ln of 1, which is 0. So ln of absolute value of L. And note that ln of 1 is equal to 0. So I'm not going to write this down. The limit of ln of infinity, this is equal to infinity. So this area, the area gets larger and larger. It's not a fixed number like previous example, which was 1. So this area is infinity. For this integral, the area below this function is infinity. So as you can see, you're dealing with two types of areas calculations when it comes to improper integrals. Sometimes it converges to a nice number, like previous example, 1. Some other times it diverges to infinity. So when it comes to improper integrals, we're dealing with two types of integrals. If the limit exists, we say that we have a convergent integral. If the limit doesn't exist, or it's going to infinity, we're dealing with divergent integrals. So for improper integrals, if the limit exists, we call it convergent integral. If the limit doesn't exist, does not exist, we call it divergent integral. integral. Convergent, divergent. Like the integral 1 to infinity 1 over x squared dx is convergent. As you saw, it converges to 1, and the integral 1 to infinity 1 over x dx, it was infinity, the limit doesn't exist. So it is a divergent improper integral. What's the use of improper integral? You're going to see this in next calc class when you're dealing with series. Very well. So far we learned that if we have the integral of 1 to infinity, or in general a to infinity, of function f of x dx, use the limit of the integral a to l as l approaches infinity for function f of x dx. If you have negative infinity to be of f of x dx is going to be the limit L to b as L approaches negative infinity. Limit of the integral LT, any other variable that you like to use, as L approaches negative infinity. So I expect you to ask, what if it is negative infinity to positive infinity? If you have an integral like this, negative infinity to positive infinity, f of x dx, well, you can separate this as the integral negative infinity to a f of x dx plus the integral a to infinity f of x dx, then apply 1 and 2 for these two improper integrals. Very well. So let's talk about arc length. Another use of integral is to actually measure the length of graphs or arcs. Objective arc length. This is chapter 8, 8.1. Very well. Suppose you have a function y equals to f of x. Let y equals to f of x be a function defined on closed interval a to b. Suppose the derivative of the function over the interval is continuous. Let y prime be a continuous function on this interval, a to b. Then the length of y equals to f of x is denoted by L equals to definite integral a to b square root of 1 plus the derivative raised to the second power dx. Okay, new formula, calculating the length of the arc. So suppose this is your graph, y equals to f of x, and just one piece of this graph bounded between a and b in xy plane. Well, of course, we're not going to use a ruler to calculate the arc length. It doesn't make sense. Should I take a ruler and start measuring this from this? Okay, this is this length, this is this length. So what we're doing instead, we're using the Riemann sum by dividing this guy into small pieces and then using the summation notation as these small lengths on x-axis are getting smaller and smaller. The delta x converts into dx, and we get our proper integral, definite integral a to b of square root of 1 plus y prime raised to the second power dx. Later on in next calc class, we're going to see that we can write L as integral a to b square root of 1 plus y prime, or the derivative dy over dx squared times dx. Then we're going to simplify this radical this way, which is equal to the integral a to b square root of 1 plus dy to the second over dx to the second dx. And this is the integral of dx squared plus dy squared, taking common denominator, and dx squared dx. Later on, we're going to use this formula in parametric calculations. Parametric calculation. So later on, we're going to define a new variable like time. Remember that this is a graph in xy plane. We are following the position of a particle, in each position. You have x and y, and they are following each other, and this is the path of that particle. Later on, you're going to see that we can introduce some new variables like time, why not? And we're connecting the position to the time, and we convert all of these formulas in parametric form. Very well. Suppose you have this guy here. Example, find the length of, what is our function? Y equals to x to 3/2 between these 2 points, 1 and 1, 2, 4, and 8. There we go. So recall that the arc length, L, is integral a to b square root of 1 plus the derivative of the function raised to second power dx. Okay, there we go. So everything is crystal clear. My x is bounded between 1 and 4. 1 and 4. This is my A. This is my B. The initial point, terminal point, and taking the derivative is not that hard. My prime is 3/2. X to 3/2 minus 1, or my prime is 3/2. X to 1/2. Okay. So L is equal to the integral 1 to 4 square root of 1 plus the derivative raised to the second. 3/2 x to 1/2 raised to the second power dx. Okay. L is equal to 1 to 4 square root of 1 plus 9 over 4x dx. Okay. This can be calculated using u sub easily. Like u with a quantity inside the radical 9 over 4x. So du is 9/4. dx, or dx is 4 over 9 du. To change this, so L is equal to the integral square root of u and 4 over 9 du. So this is u to 1/2. This gives me 1 over 1 plus 1/2 u, which is 1 plus 9 over 4x, 1 plus 1/2, and x ranges between 1 to 4. This guy is equal to, so if you take common denominator, you get 2/3, and I missed this guy, 4 over 9. 4 over 9 times 2/3, and then for this guy, we just need to plug in 4, then plug in 1, and try to simplify this. You get 1 plus 9, 10 raised to 3/2, minus, when I plug in 1, I get 13 over 4 raised to 3/2. So eventually they have to use a calculator. You have 8 over 27, 10 to 3/2 minus 13 over 4 raised to 3/2. Julie needs to use a calculator. This is the length of this. This guy in xy plane, 1, 2, 4. So you have 1 and 1. Okay, 4 and 8. And the behavior of this guy is going to be almost like this. So we calculated this length here, which is this ugly number, 8 over 27. Times 10 to 3/2 minus, let's simplify this guy, 13 over 4 to 3/2 Okay, give us more examples. Well, here's another example for you. Here we have find the length. Let me write this formula here for you. Find the length of this guy, parabola y squared equals to x from 0, 0, 0, 0 to 1 and 1. So you have initial point and you have your terminal point, and question says, hey, find the arc length. There you go. So if you want to apply the formula here, it says you have your function y equals to f of x, right? Y equals to f of x. So it means that they have to take the square root of both hand sides and then start taking the derivative. Very well. Okay. Arc length 0, 0 to 1 and 1. Y equals to f of x. So it means that our y is equal to, let's take a look at this. First of all, what's the graph like? How do we graph this guy? From 0, 0 to 1 and 1. This is our graph. 0, 0 to 1 and 1. You want to know what is this length here? So y is equal to plus minus square root of x, and y prime is equal to plus minus a half x to negative a half. Then, very well, our L is equal to integral 0 to 1 square root of 1 plus minus a half x to negative a half raised to seconds, or just 1 over square root of x. Okay. So here L is equal to the integral 0 to 1 square root of 1 plus 1 over 4x dx, or L is equal to the integral 0 to 1 square root of 4x plus 1 divided by 4x dx. So recall that if y is equal to f of x, we use L equals to the definite integral a to b square root of 1 plus y prime raised to the second power dx. What if I want to use the arc length with respect to variable y? Why not? Here you get square root of 1 plus x squared to the second power dy, and x is a function of y. Let's try this guy. Maybe it helps us to calculate this integral in an easier way. So x is equal to y squared, x prime is 2y, okay. Then L is equal to my y starts from 0, goes to 1. So this is my C, this is my D. 0 to 1, square root of 1 plus 4y squared dy, which is the integral 0 to 1, square root of 1 plus 4y squared, 4 squared, which is, here you don't have to do that, 4y squared dy. So remember the type when we have square root of a squared plus x squared, we use trig sum. Using trig sum, you can calculate this integral. So in this case, you can say that, well, here, if I just take a look at this, it's 2y squared. So if I take my y to be a half tangent theta, then you can take the derivative with respect to y. So remember that tangent is sine over cosine. Then on the numerator, you get 1. On the denominator, you get cosine squared. So you get secant squared theta d theta. Then you can substitute all of these here. Your L is equal to the integral. So here you have square root of 1 plus, you have 4, and then here you have y squared. So you can cancel out these two, 1 plus tangent squared theta, a half secant squared theta d theta. This gives you can bring a half in front of integral, you get secant theta times secant squared theta d theta, which gives you a half integral secant to the third theta d theta, which is equal to a fourth secant theta, or if we use boundaries. So if you plug in 0, if y is equal to 0, then your a half tangent theta is 0, tangent theta is 0, or theta is 0. If y is equal to 1, here you get 1 equals to a half tangent theta, or tangent theta is 2, or theta is inverse tangent of 2. And this is your upper bound. So here we get 0. Let us call it alpha, or just write it as inverse tangent of 2. So here you have a half secant alpha, tangent alpha, with a little bit more space. We need another a half, right? Yes. So we get another a half because we have outside. Not this one. Here a half. And then here we have ln of, so positive, I'm not sure, secant theta plus tangent theta, then we're going to plug in 0 to inverse tangent of 2. Then you can calculate this number, plug that in, and eventually you can use your calculator to calculate this length. Calculator to calculate the rest, and we substitute this theta, we don't need alpha. Calculate the length for you.